Thanks very much. Yeah, a quick disclaimer. We're not the first people to use expression templates with Kokkos. However, when I was going through this work, I found that there was not very much in the literature to go on, and even less on why expression templates work so naturally. So we're going to talk about that in the context of lattice quantum chromodynamics. So Lattice QCD is a first principles approach to hadronic processes. So what that means is we're looking at how quarks and gluons combine to form mesons and baryons, such as the proton, and how we can do various things with those, like look at the scattering amplitudes and search for exotic particles that we'll find in colliders, or maybe probe the structure of the proton for a couple of examples. So what happens in Lattice QCD is we take the fundamental equations that govern the dynamics of quarks and gluons, and we discretize them to a four-dimensional lattice. When we do so, the quark fields are going to reside on the vertices of our lattice, and the gauge lengths, which are the discretization of the background gluon gauge fields, connect the vertices of the lattice. Now, the quark fields are going to be at each lattice site an element of a complex valued 4x3 matrix, and then the gauge lengths themselves are complex valued 3x3 matrices, or which are elements of the SU3 gauge group. So we saw yesterday that one discretization of in Lattice QCD is the staggered kernel. We're going to be looking at what's called the Wilson kernel. So instead, our quark fields psi are going to be represented by a view that has a spin and color internal index, which are given by the 4 and the 3, and then the asterisks there are going to be the runtime dimensions of our lattice. Similarly, for the gauge lengths, they also have dimensions in each space-time direction, and the 3 and 3 are the indices for the column and rows of the SU3 matrix. And it's also very handy sometimes to work with a slice of the gauge field in one direction, so we have the third representation there. Now, we have a large motivation for expression templates in Lattice QCD because, one, the primary work that is done in any Lattice QCD calculation is the inversion of your lattice operator. So we have a very large dependence on iterative solvers, which means that there's a lot of linear algebra routines that we want to write very succinctly. In addition, we have other operations such as the plaquette, which would involve multiplication of these SU3 matrices together, and also when we're actually calculating observables, which we need to get out the correlation functions for, we have to insert these so-called gamma matrices, which is essentially a 4x4 matrix that is multiplied onto the quark fields at every lattice site. Okay, so for how we're going to do expression templates, we're not going to actually be looking at the original formulation of expression templates, but we're going to be looking at what's called easy expression templates. And so when these were first introduced, they were given the name easy ETs because they actually reduced the amount of code that you had to write, because you didn't have to write so many overloads for each of the operators that you were using. So easy ETs in particular work very well with Kokkos, very naturally. They kind of just work out of the box, and we'll see why in a second. Well, we're going to go through the ingredients of expression templates, or easy ETs in particular. Now, the first thing that you need is an interface class, and what this is going to do is it's literally just acting as an interface in your expression, but the key point here is that it actually removes itself from the expression using this explicit downcast to the template type. Okay, and this is going to come back in a little bit. Now, the second ingredient that we need is a wrapper class. So this class is going to wrap your view and it needs to also provide an overloaded access operator. So here we've defined this field class, and it is going to inherit from the expression class through the curiously recurring template pattern. And also you can see here that we're providing it an access operator, which in turn is actually going to return that element of the view for the particular index that Kokkos is going to supply it. The third thing that we need is the operation class, and this is actually what is going to perform the magic here. And this too is inheriting from the expression of the interface class through CRTP. And this is going to return the element-wise result of the evaluation of your expression. So for this example here, this would be an operation class for the addition of vectors. And what we have here is we've also given this a access operator. And what that is going to do is it's going to perform the addition, but it's calling the access members of the types of E1 and E2. So if E1 and E2 are two fields, then what that's doing is it's calling the access operator of the wrapper class, which calls the access operator of the view. And by that way, you get the addition of the view element together. Now, we also need to provide an overloaded arithmetic operator. And so this is really where everything works out very nicely with Kokkos. So this is going to return an object of the type of the operation class. So in this example here, we're overloading the addition operator, and it's going to return an object of field add. But you can see that here we are actually using this explicit downcast function. And this is where the interface class is removing itself from the expression. So what's happening is when this is performed, you have no host functions remaining in the expression. And this is really critical for how Kokkos handles the shallow copy to the execution space. Because once that happens, you can't have any host functions in this expression. Otherwise, you get a crash. Now, the last ingredient, which is not actually part of the original EasyET, but this is specific to Kokkos, is we need to have an overloaded assignment operator. Now, this is where we're going to perform this in parallel with a parallel for. And again, we have this call to the downcast function. And so the last encapsulating interface is going to remove itself again. And this assigned field is just a functor, which is going to just set the expression to equal to the target. And then all of this is going to be done in parallel under a parallel for. OK. So we'll look at some results. This is an effective memory bandwidth benchmark. And we're actually going to be comparing to there's a very popular Lattice QCD library called Grid, which is very, very highly vectorized. It's very optimized. It also has offloading to accelerators. They've done a lot of really good work with this library, so it's a really nice thing to try to compare to. So what we're comparing here is the stream benchmarks of add, scale, triad, and then we have our SU3 times SU3 multiplications. And for the most part, we're doing pretty good. We're pretty happy with the performance considering how optimized Grid is, except for our SU3 times SU3 routine, which is way down at the bottom there. On the right side of the plot, we just have a zoom in on the sustained memory bandwidth region. And I should say that the dashed horizontal line there is the measured sustained memory bandwidth from the stream benchmark. But overall, we're pretty close to grid, except for our SU3 times SU3, and fairly happy with that. Now, this is the same benchmarks, but performed on A100. And again, we see some fairly good performance. And again, we see that our SU3 times SU3 routine needs some improvement there. I should also mention that for all of these routines, we do use a heuristic for the tiling, which involves the lattice extent. So in the case of the execution on the AMD epochs, we have the tiling uses the lattice extent in the two rightmost dimensions. And then for the GPU, it's using the lattice extent in the leftmost dimension. So it's not a completely optimized or optimized tiling for these, which is something that we would like to do in the future. And just to flash the acknowledgements screen to say thank you to all my collaborators and the funding. Thanks.
Thank you. And any questions while the next speaker sets up? I mean, I'll ask the obvious question. Why are the results for S3 not as good? Why do you think?
So I think that there could be a couple of reasons. It may be necessary to actually use a temporary to store the results of the summation over rows. And then on top of that, because we're doing element by element access, there's a lot of indirection that is actually happening with the overloaded access operators there. So if you think of the matrix multiplication, you're having an access on each element, and you're now doing it on an expression, which is then doing it on the wrapper class, which is then doing it on the view. So there's a lot of indirection happening there, which might be part of it.
Where can I get the code if I want to play with it?
Sorry, what was that?
Where can I play with the code if I want to see how you implemented all that?
Right now,